welcome to all of our speakers for this session. So welcome to Mengi, to Catherine, to Alejandro and to Phil. Hopefully you'll all be able to share your screen once we get to the point for your presentation. Any problems at all, just give us a message in the chat and we'll get things sorted out. So this session has been organised by Daniela Castro-Camillo and myself. We're both based in statistics at the University of Glasgow, but we've organised this session on behalf of the Environmental Statistics section of the Royal Statistical Society in the UK. So we have 4 wonderful speakers for you all online as part of this session, illustrating statistics and data science in terms of impacts of climate change from a UK statistical perspective. So we have Mengi from the Data Science for the Natural Environment project at Lancaster University. We have Catherine from the UK British Geological Survey. We have Alejandro from the Alan Turing Institute in the UK. And then last but not least, we'll have Phil from the UK Met Office. For all the speakers, you have 15 minutes for your presentation. And so we'll just take all the presentations first for the sake of time, and then we'll leave questions until the end of the session. So for anybody online, if you want to post questions in the chat, then Wesley will keep an eye on them as we go through the session. So without further ado, Mengi, I will pass over to you. And if you want to try and share your screen, please.
Thank you, Claire. Can you hear me okay?
We can, Mengi, thanks.
Yeah, I'll just share my screen. Okay, can you see the slides?
We've got them, that's great.
Okay, yeah, thank you. Good morning to Canada and good afternoon to UK. I'm Mengi from Lancaster University, and today I'll be talking about a project I work on, which is called Signals in the Soil. And what we're doing is to develop a change point based approach to modeling the soil moisture dynamics. And so this is joint work with Rebecca Chris from Stats and John Jessica from the Lancaster Environment Center. So start with, I just show you a picture of the soil moisture time series. So we can see here is the soil water volumetric content measured over a year in the field site in the US. We see that the time series consists of lots of spikes and then the decays. And if we zoom into one of those decay events, we would have something like this. And it's kind of like can model it using exponential decay curve and parameterized using asymptotic parameter alpha 0, which is how eventually the water dries to, and the theta, which describes the decay speed, and also alpha 1, which describes the size of the gap between the highest point and the asymptotic. And this type of model in the soil literature is called dry down modeling. And traditionally, they're done by first take a time series, then we manually segment the data. Then for each of the segment, which considered to be a dry down curve, we would fit a model like this. Then people would do some summary of the parameters, theta, and also usually alpha 0, because these are the 2 most interesting ones. And this is quite classic approach to the problem, but it can be quite time consuming and also exhausting if you have, say, a lot of time series. You have to do kind of repetitively over a large number of time series. So what we're trying to do is to come up with a more automatic method. And so for this purpose, we proposed a change point based method to solve the problem. And this is motivated by a spectrum problem in neuroscience, and one of method documented in Drew and Witten's paper in 2018. So they have a time series which have similar pattern, although in their case, the parameterization of the problem is different, and also the focus is on the timing of change point, where first our focus is on the parameters of each segment. And so just to rephrase the problem into a change point problem, so every time we have a sudden rise in the soil moisture, the spike is the time we consider as a change point. And the segment following this change point is described using an exponential decay model. So this is the model here, which is also the dry down model. And we parameterize the decay parameter theta into gamma here, so that when we do the optimization, gamma doesn't have a limit on doesn't have a bound on the parameter. And just in order to fully explore the dynamics in the temporal dynamics in time series, we assume that the parameters from each segment, it would change. So it's not static. So the decay parameter from springtime can be very different from the summertime. And this is kind of motivated also by the soil literature that we know in different seasons, when you have different vegetation, the infiltration of the water can be quite different. And so statistically speaking, our problem is to identify the change point, denoted here by tau I, and also estimate the parameter of each decay segment. And this can be done by minimizing and penalize the cost function like this one. So in the left-hand side, we have the overall cost from K segment, and then the right-hand side is penalty term, which penalize the model complexity. And in this case, we choose the penalty to be just the number of the change points. So a heavier penalty means that we're going to try to identify fewer number of change points. And in particular, in this case, the cost function is the negative log likelihood of the exponential decay model. To solve this optimizing function, we can use the dynamic programming method. However, for a very long time series, this can be quite time consuming, and it's usually in the order of the n squared. N is the length of the time series. So to improve computational speed, we decide to using the pruning criteria based on the PELT algorithm, which is PELT stands for penalize exactly in time. So just to quickly go through the idea of PELT, and for example, it begins with so we say we can recursively compute the overall cost function F. So here we have, say, the overall cost of the data up to time S can be written as the overall cost of the time point up into tau, which tau is before S, plus the cost of segment from tau plus 1 to S, plus the penalty parameter, because by introducing tau, we add one change point. And if we have, say, the cost function C, satisfy the condition that by adding a change point to the segment, we wouldn't increase the cost subject to some constant C, sometimes K, then we can prune some time point T prior to the last time point T prime if this condition is satisfied. So this basically means that in this case, if adding T as a change point would actually increase overall cost. So if that's satisfied, then we can remove the T from the recursive computation, so that at time point T, we don't have to consider everything that happens prior to time T, but we just look at the most likely change point based on this pruning criteria. So using this criteria, we can reduce computation time from an n squared to in the best case scenario, n, so the linear case, although the real situation depends on how well the data behave and also the penalty parameter we choose. And so applying this method to the soil time series, what we can get is, first of all, we can get the change point. And here is an example from a field site. And in all the triangle indicates that the change point, which corresponds to the time when the sudden rises occurs, like this one. Then we can also extract the parameter for each segment, and we can plot these parameter over time to explore their temporal patterns. So for example, here we have the asymptotic parameter alpha 0 estimated for each segment. And the gray band is the confidence interval related to each parameter estimation. And in this case, we can see that there's some kind of temporal pattern. We can't really call it seasonal because it's less than a year, but we see that the value of the asymptotic level is a bit lower in the summertime and higher in the winter time. And we can do the same for the decay parameter, although in this case, it doesn't really have very clear temporal pattern. It's just some kind of random fluctuation over the year. And we did this to multiple different field sites, and we found that actually for very different field sites, these patterns can be quite different. And we can also look at the distribution of these parameters, and they also have very different shapes. This leads us to the idea of maybe we can use some of these summary statistics or the temporal plot to study the soil signature, which is a property related to that particular type of soil or the food. And this idea, we actually took it from the hydrological literature, where people actually extract physical interpretable indices to study the property of particular catchment. And we wonder if we can do the same to the soil data. So we did an experiment using the NEON data portal, the food site in NEON data portal, where NEON is a US database they measure lots of ecological related variable, including soil moisture. And in this special case, we picked 9 food sites across US, as you can see from the plot here. They locate in very different places and they have very different climate. And just to give an example, I'll show the result from 3 of them. One is SRER, it's in Arizona in quite hot and dry desert area. Then we have also another example from UNDE, it's in northeast of US, which is colder and also wetter, and OSBS in the very southeast, which is hot and humid. So here I showed this is the distribution of the estimated asymptotic parameter. In this case, we can clearly say that in SIA, which is hot and dry, the asymptotic level of soil moisture is quite low. And in UND, which is much wetter and colder, you have higher levels of asymptotic soil moisture, whereas OSB is sort of have in the middle, and also distribution is more symmetric, whereas the other two are sort of skewed. And this is also the from the same site, but a different parameter, which here is the decay parameter. And despite all of them are left skewed, we see the concentration of the valued parameter varies. Say here you have a lot of the decay parameter close to 1, whereas in UND it's more kind of flat distribution. And we suspect this is related to the soil composition of the food site over there. So just to summarize this idea, by looking at these distributions and also the histograms of the parameters or other summary statistics, we can see clearly the things changes across different food sites. And these differences can be attributed to sometimes the climate of the food site, sometimes it's the soil composition, for example, the sand, silt, and clay content. And these distributions, along with some other summary statistics, may be used as soil signature linked to a particular type of soil in the food site. And we also suspect that if we have a soil that experience some changes, say degradation, or they're doing some restoration to it, maybe we can also see the changes in the signature. So like we can maybe use the signature to also study long-term behavior of the soil. We don't have the time or the chance to test it because the data set we look at are all experimental food site, which doesn't have they don't have disturbance to these sites. But if we have data set that experience change, it will be quite interesting to see whether we can use this method to also identify the change in the general pattern. So that's the first part of the stuff. And the last few slides, I'm just talking about the extension we're trying to make at the moment to make the method more flexible. Previously, we assumed that a time series of soil moisture is all consisting of the sudden rises and then the exponential decay. Of course, in real data, you might have more complex patterns which are related to sometimes seasons or different vegetations. So we want to have a method that's more flexible, that can choose between a collection of models, a better one to describe the segment. And for example, we might want to use exponential decay model to describe soil, well-drained soil, and maybe a mean model or linear model to describe soil in a different season when it's more saturated. We try to do this using the Bayesian online change detection method, which is basically a state space model where we can have the latent space defined as CT, which is the last change point prior time t, and also MT, which is model index of the model fitted to the segment. And the inference of that can be done by sequential Monte Carlo. The main problem we have at the moment is parameter estimation. In the original literature, they're either known or they can be marginalized easily given the prior conjugate prior. But in our case, for example, exponential decay, we don't really have conjugate prior for the decay parameter. So we need to either estimate it or kind of get away with probing some way. And most of literature don't deal with segment-specific parameter, but we found something from literature, and we decided to try the idea of augment the parameter onto the latent state. So that changed the state from change point, model index, and also the parameter. And we're still experimenting on this idea, and we're also experimenting on something about the pruning strategy to make the Bayesian method faster. And here we just like a very simple example where I applied some basic algorithm to, this is the soil moisture time series from a field site in Colorado, and where I give it to choose between a linear model and the exponential decay model. We see that, so the idea is trying to having a method that can actually identify, oh, this is the exponential decay segment, that is not, then so we can estimate the parameter better. When we do the summary, we can also have a better like quantification of the say infiltration property. Yeah, so that's everything from my talk today, and yeah, it was just a picture of the field site we work with. So thank you very much.
Yeah, perfect. Sorry.
Okay, I think we're good now. Thank you so much, Mengi. Thank you for a really interesting presentation. As we said to begin with, we'll keep questions until the end of the session just for the sake of time. So if you've got questions in the room, note them down. If you've got questions online, feel free to put them in the chat, and hopefully we'll have time to get to those later. If not, then of course you could contact the authors directly as well. So thank you so much again, Mengi, and we'll move on to Catherine next. Catherine, do you want to try and share your screen?
So hopefully you've got some slides.
We have, yeah. You're all good to go, Catherine, whenever you're set. So Catherine from British Geological Survey. Thank you.
Thanks very much. Thanks for coming along, everyone, and thanks to the organisers. It's really nice to be able to take part, even though I can't be over there with you. So just as a very brief introduction, the British Geological Survey is basically, our remit is basically anything subsurface and below. So soils, rocks, groundwater, geological hazards, and also hazards and things that we can usefully use from the subsurface. So here's some work that I have done recently with my colleague John Bloomfield, also at British Geological Survey, and Gemma Coxon and Yanchen Zheng, who are from the University of Bristol. And what we've been doing is we've been looking at changes in the seasonal patterns of environmental time series, and we're looking at base flow, which I'll introduce in a minute. Here we go. So in terms of environmental time series, if we think about a very sort of classical way of thinking about time series, we've got a model that looks like trend plus seasonal plus residual. And we often think about changes in terms of trend. Is it going up? Is it going down? Does it have some nonlinear trend? But we often sort of brush over the seasonal component. And in the hydrology literature, which is where this example is a hydrology example, the seasonal components are often thought of as being like an average component over the 3 months of a season. So as an example, what's often done in the literature is the mean of the October, November, December values are taken, January, February, March, etc. And then you essentially split your time series down into 4 separate time series. So we have a winter time series, a summer time series. So the seasonal components are often thought of in quite a kind of unconnected way. And thinking about the different types of time series we might encounter, so I've just put some example time series on the right-hand side. So the ones that I tend to think of in my work are things like base flow, which comes from river levels, but there could be many other types of time series that this work would be applicable to. And in my case, again, another example would be pollutant levels in groundwater. So to explain to you a little bit about base flow, Base flow is kind of a derived quantity. So what happens is a stream flow series, like this one on the top right, is taken and then a smoothing method's applied. And what that smoothing does is it takes out all of the kind of the spike behavior in the time series. And the idea of base flow is that the base flow is the component of stream flow that is fed by groundwater or similar sort of long-term components. So all of the spikes that are caused by precipitation events are essentially smoothed out of the series. And what we get with a base flow series is something that's got a really nice annual periodicity. And yeah, we're thinking about what information does that give us as well. So base flow can tell us about the groundwater flow into the rivers. So it's very important for susceptibility for flooding and droughts, and particularly the times of year that flooding and droughts would happen. And the data set that we've used in this work is called CAMELS GB, which is freely available. And it's got daily time series for 671 catchments in the UK. So it's got not only the stream flow time series, but it's also got quite a few meteorological parameters as well. So we're thinking about this base flow, and the question we're trying to answer is whether the seasonal component of this base flow is changing over time. And the way we've thought about doing this is what we're going to do is we're going to keep the seasonal component as a curve. So we're not going to separate it into different seasons, as in we're going to take our seasonal component as a curve for each year and each catchment, and then we're going to investigate that for changes. And to do that, we've taken the whole data set, which is over 45 years long. We split it into two 20-year time blocks, so we can compare an earlier time block with a later time block to consider changes. On the right-hand side here, I've just given the kind of the flow through going from the data to what I've inputted into the analysis. So we've taken the daily base flow series for over 600 catchments. Then we've performed some monthly averaging. And then from those monthly averages, what we've got is we've taken the median per catchment and time block. So for each catchment and time block pair, we've got a bunch of we've got a value per month. And then we've also standardized these so they all have the same, so I have mean 0 and standard deviation 1. So we've taken quite a lot of data and then sort of condensed it down into a smaller amount of data, which are essentially 12 values, so one for each month, per catchment and per time block. So we've got sort of the before and the after time block. And what we can do is we can take these 12 values and we can consider them as a curve. And what we are using here is the fun FEM approach, which was originally used for cycle higher pattern over time. And what happens is the 12 values that we get, we take them from those 12 values and calculate basis coefficients. So because we have something here that's an annual repeating pattern, we use a Fourier basis so that we can estimate it with something that is smooth, looks quite similar to the shape that we've got already, and also has a nice, obviously the Fourier basis has the nice feature that it repeats year on year, so your start and end point have a nice repetition. So we've gone from our 12 points to basis coefficients, and that's just a least squares process. And then the next step in the method is to take your basis coefficients and find a lower dimensional subspace that effectively separates those basis coefficients nicely into clusters. So, and that's done with a routine that goes through projection from the, in this case, 7-dimensional space into a lower dimensional space, and then runs through a maximization and expectation step, which essentially involves assuming that what we end up with is Gaussian points in the cluster space. So essentially, we're just taking our seasonal curves and we're trying to separate them into 3 clusters that look similar. And we have the results of that clustering on the right-hand side here. And so we have specified, in this case, 3 clusters. So essentially we have these 3 curved spaces. So our first cluster has a nice annual shape. Our second cluster has a very similar shape, but it's just shifted slightly later in the year. And similarly, the third cluster again is shifted that bit further through the year. So in this case, all of the annual base flow signals have a very similar shape, but the timing of them appears to be different across the data set. So what we've done is we've taken these base flow series from each of the different catchments, and we've clustered them based only on those seasonal shapes. And what's great about what we're getting in the results is it's quite reassuring, because there's quite a lot of spatial structure in the patterns that we're seeing. So on this slide, on the left-hand side, we've got the results for time block A, so the first time block, which was from 1976 to 95, and then time block B is on the right-hand side of this subplot, so 96 to 2015. And what we can see in both is nice spatial structure. However, there do appear to be some changes. So for the purple area appears to be growing. So these clusters were ordered according to where the peak falls. So purple was the earlier one and green was the latest one. And what we're seeing is that generally things are moving to earlier peaking clusters in the second time block. So we're seeing movements from the blue cluster essentially to the purple cluster. So that's moving earlier in time. We're also seeing some green ones. So that was in the very latest peaking cluster, moving all the way to the earliest cluster. So generally the pattern that we're seeing is that the baseflow peaks are moving earlier in the second time block. Another thing we are interested in considering, especially in my job at a geological survey, is how the geology impacts these results. So in fact, the first thing that my colleagues said when I produced these plots was, that's the chalk that's coming up in the green in these plots. So in the UK, there's different types of geology, and we have a band of chalk which pretty much aligns with the green on the right hand of the subplot that goes from the south coast and moves sort of diagonally upwards. And what we can see when we consider our clustering results to the baseflow index is that we can see that the baseflow index and the clustering results have there's quite good comparison between them. So we're seeing that the later seasonal shapes, so those in the higher numbered clusters, kind of relates to having a higher baseflow index. And baseflow index is a way of considering how much groundwater is contributing to the stream flow. So how much of the stream flow is kind of a steady state. So it's really nice that we're seeing these geological controls coming out as well. And then thinking about the theme of the session, so we've got some things that are looking like they're quite clearly climate linked. So here we're considering some catchments that start off in that very latest cluster in the first time block, and actually a lot of them move a lot earlier in the second time block. So for those not familiar with the UK, these green points are the ones that I selected up here. So these are all in Scotland, and these are the catchments in the UK that have the highest elevation and snowfall in all of the UK. It's not a huge amount of snowfall, so we're only about 5% of the proportion of precipitation falling as snow, but it is the highest in terms of the catchments that we're looking at. And what we expect is that a lot of the contribution to the base flow here, so a lot of the steady state base flow, is from snowmelt from the highlands. And in fact, out of the 24 of these catchments that are highlighted, so these are just the ones that are in the latest time block to start with, 20 of them are moving to the much earlier seasonal pattern. So 20 moved to cluster 1 in time block B. And we considered why this might be. And we can see that if we consider temperature over the same periods, if we just consider the median temperature for January, it's a lot higher in the second time block than in the first time block by roughly about 1 degree over all of the catchments. We're also seeing a corresponding higher proportion of days that are above 0 degrees. So what we're expecting here is that partly that there's going to be less precipitation falling as snowfall, so there's less snowpack being generated, but also that because of the higher temperatures, the snow can melt earlier, which would contribute to the peak and base flow being earlier in the year. And just to sort of discuss the approach and the way we've gone about it here. So I mentioned earlier that we used standardized seasonal patterns. So what we're looking at is changes in the timing of the seasonal pattern, but not in the magnitude. And that's not really a criticism of using a functional data method. That's just the way we've gone about it here. So we could include also level, which would help us make further discrimination about the different base flow patterns in the UK. And then taking the functional data and clustering it does give us some quite nice indications of big changes in the timing of the seasonal peaks, but it is hiding sort of the more subtle changes, which is essentially that if something is close to the edge of being in one cluster or another, it's more likely to move cluster than one that's sort of quite central in a cluster. And we have done a little bit of looking into the functional representations of the curves before the clustering, which has given us a bit more insight into that. And as I mentioned before, we didn't include any spatial or geological information when we were doing the clustering. So we could have done, but this information that we're getting out of our clustering is purely based on the time series information, which was what we were aiming for in this approach. So just to give you a summary, so what we've done here is we've clustered our seasonal curves using the functional FEM method. And what we've seen is generally a shift to earlier base flow patterns. So this is going to be important for flooding and drought tolerance and what times of the year that these things might impact the different catchments. And obviously we have applied it to base flow, but we could apply this to many other time series. And crucially, I think what we found here is that we've found clear evidence that not all the changes in time series occur within the trend component. So it's important to think about changes in the other components, such as the seasonal component. And my email address is on the slide, should you want to contact me. Thank you.
Thank you so much, Catherine, for another really interesting presentation. Thank you so much. We'll move on to Alejandro next from Alan Turing. We can see your slides, Alejandro, so feel free to start whenever you're ready. Thank you.
Thank you. Thank you, Claire, for chairing the session. Hi, everyone. I am based in London, and today it's my pleasure to present Environmental Data Science book. That is a computational notebook community for open environmental science. This is slightly different to what you expect in this kind of conference, but it's more like a community effort to share data, models, and pipelines in environmental data science. I will explain that further. So I am research fellow at the Alan Turing Institute, and maybe for those that are not familiar, is the National Institute for Data Science and Artificial Intelligence in the UK. And recently, we are moving to our next 5 years strategy, and we are trying to cover and advance data science and AI to address these 3 grand challenges that we call. The first one is health, and we're aiming to transform healthcare and enable better outcomes for all. Second one is defense and national security, where we're aiming to protect the UK, its people, and the places they are. And finally, we have today this amazing topic about environment and sustainability, where EDS book is part of this challenge, and we are aiming to contribute to address the climate and biodiversity crisis and the need for greater sustainability. If you are very interested to know these topics and the developments of projects of community that we're building in this grand challenge, you are welcome to join a special group that we have there. You can scan this code afterwards, or I can provide later in the chat. But today, my focus is EDS book, and EDS book I can describe as a living, free, and open online resource to showcase and support the publication of data, research, and open source tool for collaborative, reproducible, and transparent environmental data science. Basically, this was incepted during my postdoctoral during that I started 2 years back. And initial purpose was to have a kind of platform where researchers of my project were able to communicate and have demonstrators of their science. I've been collaborating with people who are doing urban models, or more about forest areas, or more in like the cryosphere research. So the purpose was to have a platform where they can have these demonstrators that are reproducible, scalable, and shareable. So, and the idea is that this kind of demonstrator, people can start new ideas. And later I will show the latest version that we have this initiative, but all start like that with this purpose. So the mission of this book is to educate and leverage good scientific software and data management practices among environmental scientists through peer-reviewed, findable, accessible, interoperable, and reusable, fair, executable notebooks. This is a very strong component of our initiative. All the notebooks have this fair component, so it's something that I will explain later how we are achieving this. And our vision is environmental scientists work collaborative to demonstrate and communicate their science through fair executable notebooks, and have gained significant skill to publish in notebook-based scholarly publication systems. So there is a trend in the future that journals are aiming to adopt more digital practices, and part of these practices that people can create interactive computing narratives where they can have their normal tests, and you can reproduce and see how they generate these figures. So there are a certain component of this digital infrastructure that where notebooks are going to play a fundamental role on this. So we are training environmental scientists to learn about these technologies. So main motivation is like me during my PhD, I found many notebooks out there in GitHub. That is where you have more this kind of format. And one of the problems that I have during my PhD is like I wasn't sure if this notebook was well documented, if I have enough narrative that people or myself can get back in the next 2 years and check what I was doing. So in order to improve the quality of these kind of formats or notebooks that are out there published in GitHub, the idea of the environmental data science book is to create a community where you can improve the narrative, you can improve the visualization, and our role as a maintainers of this initiative that is open source is to make sure that you can edit this notebook and have enough metadata and the software requirements and right to people can reuse for their own purposes. And that's why in this illustration you have these different customized books or versions where people can play and use their own data in these notebooks. Maybe if you are not aware about JOS or JOSE, these are two open journals initiatives for publishing software. And essentially we are adopting a model to publish these notebooks with these different stages. Like we need some preparation, and we have different roles for this. We have author reviewers, we have editors, and we have community. The role of community is very relevant in this case because people from the community, like you, environmental statisticians or data scientists, they have an idea and they say, I have this data, but I don't know what to do. I have these kind of methods. I would like to do this notebook about this method. So you can start with this notebook idea. And we have this other steps where you are aiming to improve the idea and have the publication, and as well the community can validate and improve the version of the notebook and adding new technology, new packages to visualize the data. So all these are notebooks that are evolving over time, not just one single time publication. So that's why at the moment we have this website where we have our gallery, and basically this gallery have each of the notebooks across exploring data sets, exploring models, exploring as well some pipelines, and all these notebooks share a common template or that we provide to the people who would like to publish notebooks here, like title. We have some tags, we have some badges indicating the license. You can launch that in Binder, that is a service in the cloud for free, where you can explore notebooks. We are checking that they are working through some GitHub actions that you can check that they are working. And very important about the notebook is that everyone can see which was the first version, and how can see as well the review. It's an open review system, so people can see the first and the last version and can see the process to achieve the latest improved version through the collaborative review process that we have. Finally, we have this FAIR and DOI badges. Essentially, this FAIR is achieved through a platform that allows us to check all the metadata of the notebooks, and as well mapping all the tools, the bibliography, the input data, the outputs, and we are doing that to Rojo. I won't provide details of that later, but if you are interested, I can provide this later, and you can generate DOIs through this Rojo platform, and the rest maintains, as I say, a regular template like there. And key achievements that we have today. So through this initiative that they started almost 1.5 years back, we already provide guidelines or templates to how to publish the notebooks for the community. At the moment, we have 10 notebooks, and it's going to increase to 13, 14, because later I will explain you something very nice that we have in partnership with the climate science community about producing notebooks. And very important, we are creating this FAIR concept in notebooks that people can trace which are the initial version of the notebook and can check which is the latest version, thanks to this technology where we are archiving the notebooks. And we've been creating some community meetings in the past where we were discussing key topics with the internal researcher, but now it's open to everyone to discuss how we can improve data sharing practices, or how to share models, all these things happening during these community and co-working meetings. This is a recent activity we run this year, and we were part of a hackathon that was with the climate informatics community. And basically, the topic was reproducibility. And essentially, we have 7 teams that during a month period, they're aiming to reproduce a paper from the Environmental Data Science Journal at Cambridge University Press, that is hosted at Cambridge University Press. And they are meant to produce like interactive notebooks to check how they get closer to the results of these original papers using the same data. As part of this activity, we have some speakers training the participants about open infrastructure, scientific software, and open science. And very important is that all these notebooks are still in the process of being published, and they are going to be there in the platform. So that's why I was saying that these numbers are going to increase, and all of the notebooks are going to be DOI tagged. And the winning team received almost £500 in this Cambridge University Press book. That is the University Press publishing company that we partnered as part of the challenge. We have a diverse amount of people contributing, participants, reviewers, guest speakers, as I say, and basically it was supported by the Turing, CScale that provides cloud resources, Cambridge University, and Simula Lab in Norway. Okay, I guess it's good that I now show you something about the EDIS book, about the review process. So that's why I prepared a kind of video. Let me know if you can see the video, but essentially I will go through a demo and about the platform that we have at the moment. So this is the website. We have this landing page where essentially in the landing page, we have a kind of subset of the gallery. In this case, you will see only 3 notebooks, but the full gallery have at the moment the 10 notebooks that I mentioned in the presentation. And we have notebooks of different flavors. If we go to the first notebook, it's more about exploration of existing data set hosted in the Stack catalog. That is a kind of a catalog of spatiotemporal data. And here you can see how more or less how this notebook, you can interact with that. In this case, this notebook was authored by a reader from King's College London, and he was showcasing a land use data set in Brazil. And you can see something that we are aiming to highlight in this notebook is that the illustrations or graphics are very interactive. So that's why in this particular notebook, he was showcasing that. And of course, we are providing this how to make citation on this notebook. So very important here is about you can check the review process. And I won't go in very in detail, but you can check how this review of the notebook was performed through GitHub. And you can see all the transparency of the conversation here through a third-party application that we are using, that is Review MB. This basically, you just need to log in with your GitHub account. In my case, I'm here showcasing how you log in with this, and then you can facilitate this review through this platform. In this case, in this demonstrator, it's taking longer because it's loading all the conversation from the past. But the good thing about this platform is that all the conversation is archived or pushed back to the GitHub tab. So you can see all the conversation here. I will move further the video because I have another example of another notebook that this is from a deep learning model that we have there. And basically in this demonstrator, we are facilitating to see and explore a deep learning model that was published in a Nature paper. You can see here by Tom Anderson from BUS. And he has a kind of very interesting figures that we, in this paper, in this notebook, we replicate these figures because we weren't using the same data. We were in somehow approximated to the same figures with different data. And basically very important about the notebook is that we provide details that we are cloning the original code base of the repository here in this notebook. And you can see here the same project structure that I mentioned you in the slides. Maybe I would like in this demo demonstrate that we approximate to some of the figures that you see in the paper, but in this case they are more interactable figures. That is the purpose of these notebooks, to be more interactable. Okay, I guess I will stop my video there because time constraints. But let me get back to the presentation. Okay, so main things that we would like to do in the future about this initiative is like, in terms of the core features, we would like that the notebooks have more annotations. It means that you have more rich metadata of which is the software requirements inside the notebook file format. We would like to improve the health checking. I mean, this means like you can, at the moment, these GitHub actions that are checking that the notebook are working, we are launching that manually, but we would like to have more in automatic manner. The front end, we would like to improve the user experience, and the gallery and tags is something that is work in progress. We would like that notebooks are a way that people can communicate their science not only to scientists, but as well to decision makers. So we are thinking that we can have one narrative for scientists, one narrative for decision makers, and we can create these very light notebooks where we can inform for both target audiences. Just clicking one button and you just change the kind of audience that you want to communicate in your notebook. We would like to have more use cases and other notebooks. Most of the notebooks are in Python, but we are supporting notebooks in R, in Julia, and JavaScript. And same as we achieve with the climate informatics community, we would like to have this kind of hackathons on reproducibility with other communities like environmental statisticians like you. That would be something great to have in the future. And in terms of all this achievement, it's not only myself. I've been leading this, but this is highly inspired by other open research community, including Pangeo, that is a geoscience community, a global community, Turing Way, that is a data science in general community about good practices and ethical and collaborative data science. And we've been growing as a community. We acknowledge all people who contribute as authors and reviewers. And as well, at the moment, the results being mainly visited in the UK and the US, but we have some readers in other areas of the world. If you want to read more or learn more, you can access to any of these links and communicate through these different communication channels. Thank you.
Thank you so much, Alejandro. That was really interesting to hear about the EDS book, a great way for the community to share case studies. So thank you. And we'll move on now to our final speaker for the session, Phil from the UK Met Office. So Phil, we can see your slides. You're good to go whenever you're set. Thank you.
Thank you, Claire. Nice, thank you. Claire and Daniela for inviting me back to TIES. I first got involved with the RSS committee at a TIES conference a few years back, so it's very nice to be back. I'll just apologise, I'm going to have to leave very promptly at the end of this, but I'm more than happy to take questions by email. So this is actually work I did at the University of Exeter, primarily with Donald Cummins, who's now moved on to CNRM in France. And it was mostly motivated by these plots that I'm sure you're all familiar with from AR5, the IPCC report, showing their GMST projections. Now, this is the main quantity we use to communicate policy, climate change to the public and policymakers, but there's quite a lot of sort of shortcomings and problems with these plots, starting with the just observations are really only used as an offset here or a reference. So you pick a period, a reference period shown by the two dashed lines here, and you center all your model projections on that. Each line here is a different projection from a different CMIP5 model. And so some of the repercussions from that, depending on what reference period you choose, the spread of your models in the future changes. Well, that's not all that helpful. And you can see going back into the past, also evidence of we're not probabilistic reliable here. We're spreading out again going into the past. Now, there's explanations. You might expect uncertainty to go up in the past as odds become more sparse, but that's not what's doing it here. So we wanted to try and do something a bit more of a theoretical basis that we could claim might be probabilistically reliable. So fairly straightforward statistical approach, formulate a time series model for the climate model output, fit the time series model to the CMIP models, use the CMIP fits to find a plausible range for the time series parameters, use that to constrain a time series model fitted to observations, project forward. Straightforward, right? So the first, when we sort of floated this to some of the climate guys, the first question we got back was, well, how do we justify the time series model? So we went away and had a think, and we kind of called their bluff on that one. So we're going to embed the very simplest form of climate model, which is represented here. They're called box models. And we're going to embed this into our statistical model. So a box model, if you never come across one, the different boxes here, the top one is basically the surface of the Earth. The lower boxes are shallow and deep sea levels. Basically, their heat capacity is defined by the parameters C. We've got some forcing heat coming in F, which is what we fit at the surface. N here is the top of atmosphere radiation that we're getting from the sun. These are very simple, but they're still over parameterized. So you need this top of atmosphere observations to fit them. Couple of other problems. When we think about fitting them to observations, we don't have that. Well, we can get around that by essentially integrating over the forcing. Once we've got parameter ranges from the models, the signal in the observation, the climate change signal in the observations is often very weak. So these models are usually fitted to quadruple CO2 experiments in order to get enough signal to actually get decent estimates of the parameters. But again, that's why we're fitting to the models first, so we can narrow down that parameter space. The lesser known problem that we identified, because these are used quite widely, is that if you fit one of these energy balance models to one of these quadruple CO2 experiments, and then you say feed it with forcings from something like RCP 4.5, a more reasonable climate change scenario, the projections are biased. So they don't always do a good job, these simple little models, for all their elegance. So this is an example here. On the left, we've got temperature. On the right, we've got the top of atmosphere balance, radiation balance. So we fitted energy balance models to these abrupt quadruple CO2 outputs, and then projected forward the RCP 4.5. The red lines here are the mean and credible intervals from the EBM. And the black line, I think here is had CM3, but it's just a typical representative climate model. And we can see that for radiation, it's not too bad, but we're getting a systematic bias in the temperature beyond about 2000. And it's not just in this one model. Each grey line in the bottom plot here is a individual model. So they're not only individually, but collectively biased. We can see here quite badly by the time we get to 2000 onwards. Once again, the radiation balance isn't too bad. So we needed to do something about this bias. And our inspiration for how we tackled this actually came from these spikes you can see in the data, which some of you might already have identified as volcanic eruptions. So we wanted to try and model the volcanic eruptions to start with. So the forcing term in these box models is usually models as a function of CO2. This is the common form for it, basically just a function of log CO2. We expanded that to allow for volcanic forcing, which we represented using data on stratospheric aerosol optical depth. It's commonly used in the volcanology community. And so when we sat down and thought about it, we were like, well, if we can model this discrepancy that we're seeing due to the volcanic eruptions this way, could we do something similar for the discrepancies that's causing these biases? We can maybe and still interpret it as a missing component of forcing, or a missing response of each model to forcing. So we added in yet another term to the box model. They're getting a little less elegant now. A discrepancy term, forcing discrepancy. And we modeled it as the sum of a shared part, because we had that shared discrepancy where all the models were biased, and a model specific part to allow each model to be different. And these are essentially modeled as, when we move to discrete time, random walks. So what I should mention here, when I say we're embedding these climate models into a statistical model, you can actually show, it's a lovely bit of math, that in discrete time, these box models are just, so a K-box model is equivalent to a ARMA K-1, K-2, I believe it is. So there's a nice duality there between the models that lets us embed them really easily in a statistical framework once we get over these inferential problems with them being over parameterized. It means the climate guys can't really argue with us too much, although they love to try. So it's an outline of the inference off the back of that. So we have a vector of EBM parameters representing each model. We've got to assume that those parameters come from a common prior distribution. So we're assuming our models are exchangeable in Bayesian terms. We're going to learn the parameters of the individual models and of their prior by fitting to climate model outputs from these really strong 4 times CO2 experiments. So we've got plenty of signal. And then we're going to learn this missing component of forcing, this behavior of the bias term, by simultaneously fitting to historical and future outputs from different climate scenarios, so RCP 4.5, RCP 8.5. We're going to relate this to the real world by assuming that the OBS, so the real world, come from almost the same distribution, but not quite, because the real world isn't just another climate model. It's got a bunch of processes in it that climate models don't have. It's continuous, not discrete, etc. And just by adjusting this kappa parameter, we can start to allow for a bit of that uncertainty, although it's not terribly sensitive to it. We're then going to learn the EBM parameters for the real world by fitting to observations, conditional on this missing component we've learned from the models, to adjust for the deficiencies in the EBM, and then we can project forward. So get onto the interesting bits. So in a perfect model comparison, so leave one out, cross-validation, we fit to all the models except one and then project the other one as if it was OBS, we now see that ADCM3 is mostly within the credible interval. I could have cherry picked a better example, but I wanted to be honest here. But when we look at all the models together, they're now almost perfectly reliable. If they're reliable, they should lie within this roughly 2 standard deviation window. And if anything, the radiation projections are now slightly underconfident. So we're happy that in a perfect model setting, this is doing roughly what we hoped it would do, which gives us some confidence in using it to project the real world. One of the things you can get out of these EBMs that they're very commonly used for is to fit the equilibrium climate sensitivity parameter. So this is the amount of warming for a doubling of CO2. Should have remembered to look up the definition again, because I haven't thought about it for a while. We don't get a lot of constraint here, as there's only a weak signal in the observations. Normally when people use it for this, they're focusing on this one parameter, so they get a bit more constraint. But I just wanted to show that it could be used for this. But the reduction in uncertainty in the projections compared to the IPCC and the difference in the projections is quite striking. The projections really are usefully constrained. And compared to other estimates, we are slightly below, we're well below in the median warming under RCP 4.5, and we have one of the lowest levels of uncertainty of the contemporary projections. Looking at the probability of meeting the targets in the Paris Agreement, probability of exceeding 2 degrees above pre-industrial average is reduced to about 0.67 compared to 0.87 in the IPCC estimate. That's with a bit of smoothing on the curve. This plot is individual years. Things aren't so good when we look at the 1.5 degree, but I think everyone's starting to accept that we may not be able to achieve that. So we're probably in line with the current thinking there. We also had a look at CMIP6, although we concentrated on CMIP5 because CMIP6 is known to have a number of models with high equilibrium climate sensitivity. And that's what we found when we looked at that parameter. And as you'd expect, then the blue CMIP6 fits are quite a bit higher than our CMIP5 fits or the IPCC CMIP5 projections even. And consequently, the probability of meeting the Paris Agreement is a lot more pessimistic, but I would be inclined to believe the CMIP5 projections a bit more than the CMIP6 due to those high equilibrium climate sensitivity models. What I should say there is that with CMIP5, there were 24 models that had the data we required to fit to. We fitted to 13 that we chose to be so that we didn't have too many duplicates from either the same center, so that they'd have very similar parameterizations, or too many models that shared whole oceans, atmospheres, that kind of thing, again, to try and make sure that we had something that looked like an independent or exchangeable sample. There's sensitivity analysis to show what happens to that as well. So that's about it. So we have a physically motivated framework for projecting GMST, embedding climate models within statistical models. And we get around the problem with biases in EBM by treating them as a missing component of forcing, and achieve some fairly sizable reductions in projected warming and uncertainty. And this seems to be an approach that's we're not the only ones using it. Richard Chandler is doing something not a million miles away in the Cordex ensemble. So we're quite excited about this. Thank you very much.
Thank you so much, Phil, for another really interesting presentation. Unfortunately, I think we're a bit out of time for this session, so we need to split in the room into 2 separate rooms now. So I don't think we've got time to take questions, but please, can I just encourage everybody, if you've got questions, please either to email the authors or to take Wesley up on his offer for the networking platform to put questions and collaborate with people on there. So I'll just take the opportunity to thank all our speakers again, Mengi, Catherine, Alejandro and Phil, for a great session representing the UK and the environmental statistics section of the RSS. So many thanks.